I'm going to be talking to you about machine learning with ontologies as part of the Ontology Tradecraft seminar I'm teaching. Welcome. In particular, as you see in the outline, we'll be talking about starting off with the foundations of modern AI, leading into machine learning, then deep learning, and then we'll look at a Python library that lets you interact with logical axioms and OWL that you'd commonly see in ontologies and have that ingested through machine learning pipelines, using it as data for those pipelines. So before we get there, let's talk a bit about AI in general. You see, here we are. Nice little Venn diagram. You've got artificial intelligence as this broad scoping discipline, subdisciplines of it being machine learning and then deep learning. We're going to talk about each in turn, starting with the top. So great way in, I think, is to encounter this question and reflect on it. What exactly is intelligence? It's a nefarious topic. It's tricky, ambiguous, uncertain. I'll give you a second to think about what it means, but not too long. You can pause the video and reflect at your leisure. Here, we'll have something of a high-level characterization, enough for us to continue our conversation, that is. And it's helpful, I think, to point back to the psychologist Spearman, who promoted or provided something of a general intelligence metric that we know and love or hate, depending on. But what he was showing is that there seemed to be, according to test scores, some correlation across different subjects, some common unifying general intelligence, or G, some faculty there that you could see manifest across different metrics that you'd see according or based on these subjects. And so he had postulated the idea that there was some kind of unifying intelligence here. It's kind of a moment in the history of psychology that kind of supported the creation and exploration of more literature and research in this area, which we see today. So I'm not saying that is all intelligence is, of course. Intelligence is much broader than that, but at least it gives us a way into thinking about how we might think of intelligence. I will note, it's possible, and when you're thinking about intelligence narrowly construed in this way, to train yourself in these. It's possible to increase your scores on these general intelligence quizzes that you'd see or test. I don't mean the ones online, although for sure you can train yourself on those as well, but even the Raven Matrix scores, they are trainable. You can increase your scores on these, but I suspect there are other aspects of the way we as humans engage with the world that might go beyond such metrics, perseverance, grit, etc., things that are associated more with success than just raw intelligence, might sometimes go under the heading of intelligence. I think often do. So even if you're one of those folks who doesn't do so well on those standard metrics of intelligence, you might nevertheless count as plausibly intelligent in many other ways. And the other direction holds as well. Even if you're quite good at taking tests, you may not be so good in other areas that would plausibly be counted as intelligence. So this is just to say what I'd said at the beginning. Intelligence broadly construed is quite a bit messy. I think we know it when we see it, though. Or do we? That'll become a little clearer, or like the kind of point to that question might become a little clearer as we think about this. What is artificial intelligence? What counts? Do we know it when we see it? Intelligence per se, or do we know it when we see it? Artificial intelligence. Lots of folks have thought that we could provide definitions of artificial intelligence, and perhaps we can, but these are some that you'd see just scouring the literature. The automation of activities that we associate with human thinking, activities such as decision-making, problem-solving, learning. There's one. Another is the study of mental faculties through the use of computational models, or perhaps the exciting new effort to make computers think machines with minds in the full and literal sense, or a field of study that seeks to explain and emulate intelligent behavior in terms of computational processes. Don't worry, there are more. The art of creating machines that perform functions that require intelligence when performed by people, or the study of computations that make it possible to perceive, reason, and act. The branch of computer science that is concerned with the automation of intelligent behavior, the design and study of computer programs that behave intelligently. These programs are constructed to perform as would a human or an animal whose behavior we consider intelligent. Again, these are characterizations of artificial intelligence, which you can see in the literature if you just Google or just search around. Not uncommon. They are varied, of course, as intelligence is, artificial or otherwise. Nevertheless, they do have some common features, I would say, and it's not too challenging to pull those common features out from these definitions of artificial intelligence or intelligence in general, among many others. So for us, we'll understand artificial intelligence as a multifaceted phenomenon, much like intelligence. And some of the themes that seem to come up in literature around both artificial intelligence and intelligence include things like ability to learn, the ability to plan or reason, the ability to communicate, and indeed the ability to reason probabilistically. Let's take these in turn. You can see what I'm about to describe kind of reflected in the history of artificial intelligence. So learning, which will occupy a lot of the conversation today as we delve into machine learning, is very important even from the early days of artificial intelligence. So you can cast your eyes back to AI imitating neuroscience. What you see here is a little diagram, a little picture of a neuron, a human neuron, with dendrites and a nucleus and axons and synapses between the dendrites and axon areas. And so lots and lots of these comprise or constitute our brains, all these things firing and shooting electrical impulses that cause me to do things like speak or drink coffee or misunderstand things or understand things, kind of characterized or at least grounded in this material base of these neurons as the story goes. Again, early on in the history of artificial intelligence, there was a push to see if we might simulate what's going on in some ways in the human mind in our computational models. You see the McCullough-Pitts neuron model, which underlies a lot of contemporary learning with weights and nodes and edges. We'll be talking about those in just a moment. But you can see kind of, at least pictorially, and indeed in implementation, relationship, or at least inspiration from our architectures. The idea being here that, if we want to understand or really create artificial intelligence, then we know our intelligence. We know that we're intelligent. Let's try to simulate in our representations and our models what we're doing as closely as possible. So if we have neurons, we should have something like neurons in our computational systems and our artificial intelligence, and maybe we can train or figure out a way to train intelligence into those models just the way we do at our parents' knees. Neurons in neuronal models. On one hand, we have that biological neuron with bodies and axons and dendrites, each one being in like a firing state or a resting state, where neurons fire if the total incoming stimulus exceeds some threshold, and synapses being these thin gaps between axons and dendrites that facilitate signal exchange. That's us, the biology. On the other hand, we have something like the artificial neurons, perceptrons being an example of this, inspired by like the connectionist paradigm, where the idea being that intelligence emerges perhaps from networks of simple connected units rather than something like symbolic manipulation, where we just kind of know what should go in the model, and consequences that fall out of that will seem intelligent. This is more or less an emergent or an approach to artificial intelligence where intelligence is emergent over broad networks of lots of data and connections. You'll see that in these artificial neural networks, which are just sets of nodes like units, processing elements, etc., where each node has inputs, outputs. They perform simple computation according to some node function, and those connections, the edges between the nodes, are weighted, giving some structural architectural net, and where those weights determine what's computable by the artificial neural network. Now, I'm going to give an example of this. You can see here just a simple, very simple one. You have inputs x1, x2, x3 that can be 0 or 1. They're inputs to the node, the neuron as it were, with that little theta on the inside of it, which I'll say something about in a moment. The neuron here will fire if if one, or a one that is, if the sum of the three inputs is above some certain threshold, that threshold indicated by the theta. Otherwise, it's going to stay zero, and this is that on-off state. This is supposed to simulate that on-off state that you saw with our neurons, the firing arrest. What does this look like in practice? Well, I want to determine if I'm going to buy a lottery or ticket or should. Let's see how I might assess this or model it. X1 could be there's a high payout. Like, the Mega Millions is way up there. It just makes sense to buy. And, I want it. I have the money, X2. I have sufficient funds to purchase a lottery ticket. And X3, I'm just feeling lucky. And in general, I do. So this is not implausible. Let's say we'll set the threshold here to 2, which is to say if any two of those conditions are met, I'll buy the ticket. So, the implicit understanding here is that X1, X2, X3 each count as 1. If I get at least 2 of those, then I'm going to buy a ticket. Now, this is some not exactly accurate. I mean, some in the sense not only is it very simple, but not all of these decisions or all of these facts about the world or about me are as weighty as others. Some decisions are worth more than others, and then we can approach this even with a simple case like buying a lottery ticket by thinking instead of a 1 and a 0 for X1, X2, X3, something like the weighted sum being above a threshold. So for example, if I give, X1 being, a weight of like 0.75, X2 a weight of 0.25, X3 a weight of 0.25, and I just say if there is sufficient, or if there's like the weighted sum of these is above that threshold 0.5, then I'll buy that lottery ticket. Here I've got my little sample calculation, X1 equaling 1, but being weighted at 0.75, X2 and X3 giving basically no input regardless of the weight here, just as a matter of fact, which is to say I don't have the money. I don't have the money, and I'm not feeling lucky, but it is such a significant payout. Looks like I'm going to have, at least in this silly model, something above the threshold, so I will try my best to go get that lottery ticket. Will I buy it? I'll have to find some money. In any event, hopefully you can see that weighted sum on display here, and this is closer to what we're going to see later when we're thinking about machine learning training, especially in the deep learning case. But in general, neurons firing on off, weighted sums above a certain threshold, that's the point, right? And we see this as paradigmatic of learning. Also worth noting, just in the history of AI, because early on in the field of artificial intelligence, there was much more emphasis on attempting to program in as much information as we could symbolically, like very carefully, very logically, as a way to understand how or model how human learning goes. You'll see that in a second, but it'll something more akin to learning as reasoning out from facts that are known. That was more or less the running game or the going game in the field of artificial intelligence when neural nets started gaining traction. And so folks in the neural net community and a connectionist background, they wanted to be able to simulate what was being done in the more symbol-heavy or symbolic approaches to AI learning and AI modeling in general. And so they found themselves in a position where they needed to, say, represent fundamental operators of logic like disjunction, or, and so they were able to do this to some extent. You'll see here a neural model that is designed to, or is presented as the OR function, so the OR gate, which will output a 1 if x1 is 1 or x2 is 1. See how this works here just by reflecting on the truth table. So truth tables being more in that like logic-y, symbolic-y way of characterizing the world very precisely and crisply. You see here, as long as you have, x1, or as long as you have some like above a 1 threshold here, you should fire 1 because the truth table the output here, what the valuation of, say, a whole expression that has a disjunction as a connective is going to be a 1 as long as one of the disjuncts is. That is, as long as x1 is 1 or x2 is 1. In particular, you can see rows 2 and 4 result in the output of, or 2 through 4 result in the output of 1. Some columns, or summing the columns, suggests that we should set the threshold theta to 1, since the values of 1 or 2 make the OR function true, and that's exactly the right result. So if we take the sum in that third column, we'll note when it's 1, we should get a 1. When it's 2, we should get a 1. When it's 1, we should also get a 1. Contrast this with, well, before I'll note too, you can represent this in a diagram or in a plotted graph. So you can see that each combination of inputs here can be plotted, and do this with a truth table and the sum, but points on or above the boundary line are those that produce an output of 1. So you see right here, you can kind of draw a line through the inputs and separate, say, the good input or the good outputs from the bad outputs, the zeros from the ones inclusive. Now, contrast this with the AND gate. We see the output should be, it should be 1 if x is 1, or x1 is 1 and x2 is 1. And so we can see that represented in, again, a truth table. In this case, though, we'll see that what we should get is output of 1 in the event that x1 is 1 and x2 is 1. So it's insufficient to just, when we're looking at that sum column, to have only or something less than 2, because that will get us the wrong result. That will lead us right back over to that OR function. We want instead a threshold that is at least 2, because that's the thing that's going to get us to that single value, that single true in the truth table, which occurs when x1 is 1 and x2 is 1. Again, you can see this represented in a plot. Each combination of inputs plotted here. Notice the threshold is 2 in this case, which is the sum of x1 and x2. Is that right there? And again, we can separate the good cases from the bad cases, the true case inclusive on that line from all of the zeros. Now, it's important to be able to see this back and forth between the geometry and the algebra, because early on there was a criticism of perceptrons of this sort, these early neural models by Minsky. And now I will say that he wished he hadn't said this, what I'm about to show you, because he said it kind of set back the development of machine learning for a bit, and so he wished he'd been a little more careful in his presentation of the concern that he had. But it's basically this XOR gate. So this is exclusive ORs, a very often fundamental logical operator, and he claimed, I think accurately, that using a single perceptron or single neural model of this sort, you would not be able to represent the XOR gate. Now, XOR outputs 1 if x1 equals 1 or x2 equals 1, but not both. That's the key here. So if you look at the truth table, you'll get, second row, fourth row, 1, everything else is 0. Now, question, just to get your head into this, can you draw a line which separates the 1 outputs from the 0 outputs? I'll give you a second just to think about a straight line that might separate the good cases from the bad cases. And now I will start talking again. So if you want to think more about it, pause the video. Otherwise, here are the good cases, right? You might think, I'll draw a line between them. Oh, but you've separated the bad cases, right? Like you've just split the bad cases. And what we're looking for is a line that goes through, that has all the good cases on one side, all the bad cases on the other. That is to say, all of the y equals zeros on the one side, and all the y equals ones on the other. Won't work this direction either, unfortunately. And this was the observation that Minsky made. He said these neural models are not going to be able to capture something like XOR gate. Now, of course, here's a way to avoid that or get around this concern. Use more than one perceptron. Use a more complicated network of things that can get you this kind of output. Think of this in multiple dimensions rather than just this two-dimensional, like single straight line. Can you draw it between the good cases and bad cases? Let's get a little more graphical, as it were. But again, this set back research in this area for a while because it seemed like you folks were at least believing you wouldn't be able to build up from these simple models even something as almost trivial as the XOR gate. Now, before circling back to the kind of the broader scope of perceptrons and neural models that are parts of larger networks, I do think it's important to continue talking about the history of artificial intelligence, and so we'll move on to this other feature of intelligence, which is characteristic or somewhat thematic in the development of the field, namely the ability to plan and reason. Early on, it was planning and reasoning was understood in terms of logic, like initial hypotheses being the root of some search tree, branches being logical deductions from it, such as Socrates being a man, all men being male, all men are human, follows all Socrates is a male, also follows Socrates is human, and if you add that all humans are mortal, Socrates is also mortal. Logical theorists, they were called, at the early days of artificial intelligence flourishing. Some of them were able to prove quite a few theorems, important theorems, like the first 52 theorems. Proves the 38 of the first 52 theorems in Chapter 2 of Bertrand Russell's famed Principia Mathematica. That's quite an impressive feat. If you've ever opened it, it's like 5 pages just to characterize what 2 is, the number 2. So there's a lot of theorems, lots of proof, trying to provide a foundation for modern mathematics. If you haven't read it, don't. It's a slog. You shouldn't spend that kind of time. You should do something more important with your life. But it is good to know about. In particular for this, it's good to know that logical theorists, even early on in the heyday of artificial intelligence, were able to prove 38 of the first 52 theorems in the second chapter of it. What a nice, fun fact to make you very popular at parties, no doubt. In any event, this field has flourished since then, although not as much as like machine learning, which is really kind of the paradigmatic approach to artificial intelligence today. Nevertheless, automated reasoning has not died. Logicians have for decades leveraged automated theorem provers and model checkers to explore logical space, and most run by leveraging resolution algorithms or unification algorithms or Tableau algorithms, and software like Prover 9 or Hermit Owl Reasoner, which is popular among ontologists. So there are some kind of paradigmatic algorithms in the field. There's the Davis-Putnam algorithm, which recursively assigns truth values to variables of various propositions, and if a contradiction is reached, then it backtracks and tries a new assignment, essentially a brute force attempt to try true falses for all the variables in a proposition. You give it some theorems, you give it some axioms, and it just tries to make them all true one by one. It can be quite cumbersome because it is a brute force strategy. There is also an analytic tableau strategy, where one constructs a tree where each branch represents an interpretation of some proposition or some set of propositions that are then decomposed by extending branches with new interpretations on each, closing branches if a contradiction is reached, and then terminating when all the branches are closed or when something is fully open. So it's essentially a search tree where you find conflicts and close branches with conflicts, and try to find branches where things are left open after you've applied all of the possible rules you can to that set of propositions. I'm going to talk a little bit about this because it's linked up to that logical theorist tree search strategy, and it is also quite common, this analytic tableau strategy, when we're thinking about automated reasoning in the field of ontology. So I'll post this here. I mean, you'll see these slides. You can just take a screenshot, but I won't spend too much time talking about this here. These are various description logic reasoners we see in ontology circles. Go explore, enjoy, or rather than do that, I'm going to talk to you more about the tableau itself. And so Here is a screenshot or snippet from an article describing the kind of standard rules set that you'd see in an analytic tableau. I don't want to force you, because this is not a logic class, into thinking too carefully about what these rules mean, especially not in that syntax. And so I'll instead just write it up here. So what you have are 4 basic rules. The conjunction rule: if you have 2 things conjoined on a branch, then you can add both of them to that branch. You don't need to create a new branch. You can just drop them down. And this is basically just, if you have 2 things, if you have this and that, you can have them individually, independently. On the other hand, then we have the disjunction rule. If you have some C1 or C2, so 2 propositions, 2 claims on a branch, then you can add each of them, or you can break that disjunction apart by adding them each to a new branch. And so this is like a separate branch. And this is a way of, we sometimes call reasoning by cases. You can have cookies, you can have ice cream. I want to see what follows from each of those. So I'll assume on the one hand I have cookies and see what happens. I'll assume on the other that I have ice cream and see what happens. That's essentially what's going on here. So you've got the branching to break apart this disjunction to see what's going to happen in each case. And again, you're trying to search to see if you need to close a branch or open a branch or leave a branch open. There's also the existential rule. So if you have something of the sort, every x is related to some y that happens to be of a type on some branch, then you can add that every x is related to a specific constant, so a specific thing in the world. And essentially this is, as long as that thing is new and hasn't appeared on a previous branch. And what this is doing here, what this is trying to capture, is a very common sort of reasoning that we even do as humans. I don't say no that I don't know maybe who broke into my house and who messed up my kitchen. It was my wife. I don't know who did this, but I need to infer information about what's going on so that I can maybe tell the police so they have a hunch. I might in my reasoning think, well, if there was a person here, they probably would take up space. They may have brushed up against the wall. They may have done this and that, things that are not explicit or obvious in my, as I'm perusing my environment. I might want to reason about facts that apply to a specific individual as if they were here, even though I have no idea who this individual is. And so what I'm trying to do here is break out from this logical characterization of someone broke into my house and think instead of a specific person did. I don't know who that was, but they probably had various properties, and now I'm playing something of a game of Clue to try to figure out who that person is. It's important in this case that you don't already know something about this thing you're inserting on your branch, the A there, because if you know something about them, then it's not arbitrary, and it's important that we say instantiation of the existential quantifier be arbitrary, because you want to be able to swap it out and have said that I could have put B in there or C in there or D in there, because I'm basically trying to reason about it at a logical or structural level rather than on the ground with the something in the world. On the other hand, there's lastly here this universal rule, which essentially says if you have something related to something else on a branch, then and that sort of thing is of a type like C, then you can just go ahead and add that type to the branch. So again, if you have everything related to everything, and you have that asserted on your branch, and you say if that is the case, then I also would get something like CY here, then you can just add CY to the branch as well. And this is a sort of a form of modus ponens. So if P then Q, P therefore Q. So if you have if P then Q, intuitively on a branch here, and you have P, then you can drop down Q on the branch as well. So what does this look like? Connecting right up to that syntax I was displaying a moment ago but you might use this to check something like the consistency of the following set of propositions. And I'm using this in a syntax that's probably more familiar with folks in description logic settings. But what that first proposition is saying is that So there is everything, or something, I'm sorry, A is something related to everything, and F is related, and the X is and everything is an F as well. That's roughly speaking what it means. That second line is A is S related to B. That third line is A is S related to everything, and if that is the, or I'm sorry, if A is S related to everything, then Y, then Y is not, or then it's not the case that Y is an F, or it's not the case that Y is a B, and then the last one, of course, being that B is a B. So you could follow the Davis-Putnam algorithm, which I didn't really discuss here, to like kind of walk through checking each parts of these, like in a brute force way, assigning truth to, say, the first line, or truth to the second line, and seeing if you can do this consistently. That kind of would be, again, a brute force strategy. Alternatively, we could use this analytic tableau method, and I'll show you what that looks like here. So if we take this first line, we could just kind of use that existential rule that I was talking about and replace the x's here. As long as we're picking a constant, or a letter D that has not appeared on a previous line, and that's what we're doing here. So D hasn't appeared anywhere in the premise set, and so we can just kind of get rid of that existential, that backwards E, drop it off according to that rule. Now, we also can use this kind of that what we call the conjunction rule, because what we're left with is a conjunction at the top, the main connector being that ampersand. We could just break that down and like write each of those conjuncts on the same line, 1, 2. Now we can also then instantiate, again, we'll say, drop that universal off and bring it right down, and we can get rid of the y's, as long as, and we can kind of do that with any name we want, any letter we want. We can do it as many times as we want, because we're saying something about everything in the domain. All of the things have this restriction on them, so it certainly applies to everything. In this case, what we're doing is we're saying that restriction applies to both B and applies to both D. And the reason this is important is as we start looking or unpacking here, because we have S, A, B on one hand, then we can break out this conditional statement, drop it down here, and get the thing that the error was pointing out, as it were. And now we're in a situation where we're going to use that disjunction rule and break apart these disjuncts. Now we're going to have to do it in pairs. Again, the algorithm is not particularly bright, and so what we'll have to do is we'll break these branches out one by one, and we'll have to embed the branches according to this rule as we do it. Now, what I want to see here, just want to observe, we have B is a B, and on one of these branches we've already inferred that it's not the case that B is a B, and that is a contradiction, so we're going ahead and close that branch, so we don't need to pursue that anymore. Now, on the other hand, we apply that rule again, because we're breaking apart the not FB, and we're doing that, we're breaking apart the not FD or not BD, and we're doing that under the scope of our assumption that not FB. And that results directly, again, with contradiction. So we have two of these branches closed because we found inconsistency. On the other hand, we found one open. So there's just to say, after applying all of our rules, we have at least one branch that allows us to consistently assign truth to the set of propositions, which is to say this set is consistent. We found a way in which it's consistent, and we did so by applying all these rules until we couldn't apply them anymore to anything. We were like down to the base propositions, and we, at the end of that, had an open branch. Now, this is, again, only two of the types of artificial intelligence, or at least the themes that we see in artificial intelligence and intelligence. We still have two more to go. One is the ability to communicate, which is pretty important, I'd say. A lot of us like to do that. We count people as intelligent who are quite good at it. Even if they're not, we count people as quite good at it. And for a while, Folks in the artificial intelligence community were a little skeptical that this like communication would be something that was in the scope of machines' capacity. So it was an ALPAC report in 1966 that concluded machine translation was just more expensive, less accurate, and slower than human translation. This sort of changed when Dragon Dictate 1.0 speech recognizer emerged on the market. It kind of minimized the probability of error using a new technology called hidden Markov models, which I'll talk about now. So before I get there, I want to say, because this is sort of a base of these models, I want to give you a little description of what a finite automaton is. But I don't want to do it by making you think through all of this syntax. Instead, I'm just going to do it by an example. But what you're looking at is sometimes called state transition diagram. And what we're doing is trying to model states of, say, the world or states of some machine and try to describe on what conditions we might be able to accept certain statements or propositions and reject others. So how can we, again, seize out good cases from bad cases based on how we might evaluate expressions as they, say, move through states of change. And so what do I mean by that? Let's say you have an expression of this sort, 0, 1, 0, 1, 1. And I have a little state transition diagram here, and I have a description of it formally, algebraically, and geometrically right here. And at the very top, you'll see that number 1, it's describing the possible states in my state transition, Q1, Q2, Q3. And then what I have here are the values it might take on at any given state. So that's a 2, that's sigma, it's a 0 or 1. Any state could have a 0 or 1. And then what you have then on the line 3, I'm describing this function that lets you move from one state to another. And the description is this table you see. So if you're at Q1 and you get a 0, you go to Q1. Q1 and you get a 1, you go to Q2. Now, Q1 is going to be where we start. And then our accept state is going to be Q2. Accept state is if we land there after running through this expression, then this is going to be an expression that our finite automaton, our state transition diagram, can actually represent. I'll show you how that works. So you start at Q1. Look over here. It's a 0. We've got a 0 from our expression. And that brings us right back down to Q1. We didn't go anywhere. All right, well, now let's move on. We're still at Q1, and we're going to look at 1 because that's the next line or the next number. And then we're going to see what do we do when we get a 1? Well, okay, we drop over to Q2. Cool. Now let's move on to the next. 0, what do we do with 0 at Q2? We move over to Q3. What's next? What do we do if we get a 1 at Q3? Well, 1 or 0, we go straight over to Q2. All right, now we're at Q2 and we have a 1. Now what do we do? Q2, 1, right back down to Q2. So we ended in the accept state, which means this 0, 1, 0, 1, 1 is an expression that our state diagram, our finite automata, can represent. And this is exactly how it would do it with this table and this description of its possible states, end state, start state. Right there. Now, you can use this to characterize all sorts of interesting functions, like even and odd, like 2 plus 1 equals even, 2 plus 1 equals odd, 2 plus 1 plus 0 equals odd, and so forth. Now, what these are, Markov models. These are kind of the basis for Markov models, or Markov chains. They can be seen as probabilistic generalizations of these finite automatons. So instead of saying, if I'm in a state A and I see a symbol X, I go to state B, say instead, if I'm in a state A, then I have a probability of going to B. In other words, that deterministic transition function, that little squiggly letter with the table, becomes a probabilistic distribution. So roughly speaking, this is how you might update that characterization of these models, Markov model addition. So you can see these nodes, describe in these models states connected by edges reflecting the likelihood of a transition from one state to the next. So if you have a state like dry, a state like rain, you will have probabilities associated with the transition. So on the condition that it's raining, it will rain 30%. On the condition that it's dry, it's raining, or it will rain, let's see, you have a 0.2%. And we can characterize like transitions or possible transitions across these state transition diagrams just like that. Now, there's one other feature of this that was important to that dragon dictate and indeed to a lot of modeling that goes on now, and that's the hiddenness of the Markov model. So instead of describing all of the states, or at least assuming that you have access to all of the states, it's important, indeed, watershed moment important, to try to infer given what you see, or deduce, or like provide inductive support given what you've seen, to hidden states. So in a plain Markov chain, you can directly see the state you're in at each time step. But in a hidden Markov chain or Markov model, the true state of the system is not directly observable. So what you do see are observations that are caused by the hidden state or putatively caused by the hidden state. And so what do we have here? We have states like low pressure, high pressure. These are things that maybe you don't have access to, you're not sure of. Perhaps they're trying to abductive or reason or inductively reason to or about. And then you have observations about rain, dry, like is it raining, is it dry? And then you have transition probabilities between these, and then observation probabilities. So given say that it's low pressure, what's the odds that it's dry? So you got that 40% or 0.4 right there. So and this is a way again to kind of provide some way of angling or getting access to potential hidden states, maybe sussing out what hidden states might be, even if you don't have access to them and you only have some observations of the states that you have observations to. And this is important. There's a lot of implicit information in conversations and communication. You don't always know exactly in minute detail every single state or every single observation going on in a conversation. You kind of want to, be able to learn or infer or model probabilities around how a conversation might unravel, rather than try to model it all up front and deduce what's going to happen, as you might try to do in a state transition diagram representing finite automata. There is, again, here, a direct relation. It's almost odd to keep these separate, but this is kind of a ground floor for reasoning probabilistically. So it's not just about communication. It goes very much hand in hand with reasoning probabilistically, but you can see this, I think, most accurately, probably the best I've seen, not that the field hasn't moved on, but on display in full in this Probabilistic Reasoning and Intelligent Systems by Hudea Pearl. Now, Pearl's Bayesian networks in this showed how to extend the idea of hidden Markov models to every problem in AI, and just like the hidden Markov model was kind of a watershed moment for research, so was Pearl's work introducing math for causal reasoning of the sort that you see in communication, but much, much more broadly. So I did say don't read Principia Mathematica from Russell, but I would strongly encourage you to read this by Hudea Pearl. So now, key research areas of modern AI: planning and search, problem solving based on cognitive science sometimes, knowledge representation. I didn't talk much about that, but it is sort of like an underwriting current in all of the work that we're doing in this ontology tradecraft seminar, which is storing and manipulating information. It's also a very important feature of modern AI, and you'll see that again and again. You've seen that again and again. But there is also automated reasoning as a key research area, using stored information to draw conclusions. And then machine learning, which we'll talk about next in more detail, we're extrapolating patterns from data, as well as NLP, communicating with machines, and then, computer vision and robotics. And I didn't have much to say about those. They're less relevant here to this course, and at least one of them, unfortunately, hasn't really advanced much over the past decades. Though fingers crossed, I'll get a robot at some point. In any event, that's enough about the foundations of modern AI. Let's move now over into machine learning proper, right there as a subset of this broader field. What is machine learning? It's a branch of artificial intelligence based on the idea that systems can learn from data, identify patterns, and make decisions with minimal human intervention. So you see in traditional programming, the idea of program plus data into a computer results in output. Whereas machine learning, in a sense, turns this on its head. You've got output and data into a computer, and you result in a program or algorithm. This has been wildly successful, you see, in web search and finance, cybersecurity, digital assistance, and games, and so forth and so on. There's a history of successes here. 97, I remember seeing this. Deep Blue became the first computer playing system to defeat a reigning world chess champion. Like, I remember that. People were highly skeptical of it ever happening, and then it happened. And Deep Blue, became something that we talked about quite a bit. Watson, of course, in 2011 competed in the game show Jeopardy against two human competitors and won, as you can see, by quite a margin. Partly due to the machine learning background, or the deep learning, I should say, back end it was implementing. 2014, Facebook developed DeepFace, this algorithm that they claim can recognize individuals on photos with an accuracy of 97.35%. Pretty good. As well as AlphaGo defeating one of the best Go players in the world in 2016. Again, machine learning at the core of these technologies and achievements, major events. 2020 saw OpenAI creating GPT-3, and then in 2021 releasing DALL-E, and we of course know what's happened since. We've got more GPTs, more image generators since then. GPT-4, Gemini, etc. GPT-5 has already been out on the market at this point for a minute. These models are not entirely machine learning or deep learning, but they are an ensemble of technologies from the artificial intelligence field that are brought together in novel ways to create those chatbots that we love so much and can help us mitigate some of the monotonous tasks that we find ourselves typically doing, even if they can't handle some of the larger ones. So where does machine learning fit in such an ensemble, or indeed in such an architecture in a company across business? It's just a small piece. It is an important piece. You see machine learning here, but it's certainly not the only one. Definitely the field of artificial intelligence, indeed the field of software development, the field of broader software architectures and systems includes it as a piece from the top layer to the bottom, whether you're talking about storage or business logic or even the cloud and edge interface. It is just a piece, but it is an important piece. So I'm saying here, kind of like, adjust your expectations. It has wild successes, but it is a piece of the broader puzzle that has achieved such success. So what is it now? Learning and adaptation. Just as we started with intelligence and some characterizations of that, right or wrong, it's important here, I think, to get our feet firmly planted by reflecting on what exactly the learning part of machine learning might be. And so some ideas have been things like the modification of behavioral tendencies by expertise, or perhaps a learning machine, namely a machine that is one that learns. Broadly defined is any device whose actions are influenced by past experiences. That'd be quite broad. Lots of things will count as learning machines. That aside, any change perhaps in a system that allows it to perform better the second time on repetition of the same task or another task drawn from the same population should count, according to Simon, as learning or an adaptation. On the other hand, an improvement in information processing ability that results from information processing activity might also count as learning and adaptation. Again, some themes seem to emerge, but I'll ask you this instead as a way in. How do we learn? Just like when we started with neural models, maybe it's worth thinking about how we do learn. How do we learn? What do we look at? What do we get out of the environment? Or how do we, like, as humans, pick up from the environment? Um, certainly through engaging with it at least. Mimicking, reading, reporting, perhaps tutoring, as you see me doing on the right-hand side, teaching logic. Reinforcement of folks to correct them, as you also see me on the right here doing to somebody in the audience. Corrections when incorrect. Analogies, we do this, we learn by analogies and identify patterns. We apply knowledge to new problems. And also there's self-reflection, and then there's the whole logical component of deduction, induction, and abduction. I think these all go into how we learn, and they're all kind of compatible with those characterizations of learning and adaptation we just saw, even if not directly explicit. So when we're talking in our terms here about machine learning, though, we're thinking in terms of models that transform input data into meaningful outputs. They learn from examples, like algorithms are trained, and these models are learning from lots and lots of examples. And the central problem in machine learning, and indeed deep learning, is to try to learn useful representations of input data. And these, if we do that correctly, they'll get us closer to our expected outputs. So central to this is an encoding of data. So data representation. So an encoding of data, something like a color image encoded in red, green, blue format, or one encoded in the hue, saturation, value format, is just a representation that allows us to translate, that some data into another format that might make it easier to manipulate or use. So tasks difficult with one representation can be easy with others. So for example, the task select all red pixels in the image is simpler in RGB, whereas make the image less saturated is simpler in HSV. Now, see this here on the left-hand side, we have the red pixels, we can identify them clearly, our language lets us pick them out. On the other hand, we have features or qualities of combinations of RGB on the right-hand side that kind of can help us understand what saturation means. It depends on what question you're asking, which representation is best. Machine learning involves searching for these useful representations of input data with a predefined space of possibilities, using guidance from feedback. The simple idea allows for approaching potential automated solutions on a broad range of intellectual tasks like speech recognition or autonomous car driving, and those various successes that we'd already seen from groups like Yahoo and Bing and Oracle and OpenAI. They come in paradigms, this machine learning, these machine learning strategies. So something like supervised learning, unsupervised learning, reinforced learning. You'll hear these terms thrown around. The first there, supervised learning, is just where the inputs and correct outputs are provided by an agent, often in the form of some kind of labeled data and training data. Whereas unsupervised learning doesn't really give any guidance or hint as to what counts as correct output. You're just kind of trying to identify patterns with massive amounts of data. There's reinforced learning, and it characteristically involves aspects of reward or punishment for correct or incorrect outputs, respectively. And so you can see in some of these standard models these paradigms on display. So like classification is typically a supervised learning model. And in this case, you use some predefined labels on data and then rules to predict the output for future inputs. So you have some unlabeled data and a poor person sitting there labeling it. They create a labeled data set that is then used to train some model to make predictions about the future or future encounters with data. So an example here, you might assign items to one of a set of predefined classes of objects in the data set based on a set of observed features. So is this Hebrew about the Middle East conflict? Yes or no? Probably need somebody who can read Hebrew to answer that question. Tell us yes, tell us no. Then we'll input that in our corpus that we use to train for classification. Classification here being drawing lines between good cases, bad cases, or really not good cases, bad cases, but some cases from others. So drawing a line in terms of, say, weights and heights on a plot between children and adults being farther up and to the right, children typically falling closer to the 0, 0 point on the graph. Now, regression is another type of supervised learning here. One in its simplest form being to learn a function from a set of examples where you're trying to adjust that line that you're drawing through the data points on some training set. You're essentially doing curve fitting exercise. And if you're familiar at all with algebra, taking anything in the States, playing around with your TS-86, or whatever the number is now, this should not be unfamiliar to you, where you often were trying to plot diagrams and lines and do curve fitting in the algebraic context. That's essentially what's going on here. You're throwing data that has labels on it, and you're attempting to find a curve, learn a function, to find a curve that fits the data as closely as possible, whether it be just a straight line, some curved line, some really curved line, some chaotic line, under some assumptions like Occam's razor, namely preferring the simplest hypothesis consistent with the data. There's also clustering that falls more or less in the unsupervised learning category. You see here learning that involves no guidance and no hints about correct outputs. The data is raw, there are no labels. So you see on the left here elephants and giraffes and cows. Unknown output, no training data. You just blah, blah, blah. The machine does its churning, lots of processing, and then outputs the appropriate slots and categories that we would expect after the case. Unsupervised, you're just trying to like throw the data in and be clever about how your model sorts things, and then generate the appropriate outputs or clustering that you might expect. And you can see like the kind of underlying thought here is how a fish or a tadpole might learn, like a real tabula rasa, like there's nothing starting. You just kind of like encountering the world and all its booming and buzzing brightness and picking up on patterns slowly over time. All similar input patterns end up being grouped together as clusters, and if a matching input pattern is not found, some new cluster is formed. And so you can see this as contrasted with clustering here, where placing objects into meaningful groups based on similarity is characteristic of classification, and aiming to discover useful but unknown groups is more or less what happens in clustering. And so you may end up getting very similar results, but the inputs they're going to be quite different, whether they're labeled or not labeled in the classification sense, not labeled in the clustering sense. You can, and you should, for more details about this, navigate to the following site and explore clustering in detail. I've tried to put some little exercises in here from some apps that I've found, some little games, all that gamification nonsense. I think it's actually helpful for solidifying some of the material. But I'll let you pause, or I'll let you, maybe pause the video, take a moment to type that in so it's at least in your browser. So when I'm done talking, you can go check it out at your leisure. I'll wait just a minute and mumble to myself until I believe you've had time to write that down. And now I will move on because there is more to cover. So also time series analysis, unsupervised, potentially supervised, but sometimes unsupervised. And this is basically an attempt or model for analyzing data points collected over time to identify trends and patterns and make forecasts and predictions. So there's like an induction going on here that's temporally ordered, can be mixed with the other strategies that we've discussed. Seems like it has been an important enough field where we're using its own diagnostics to be called out separately as an ML strategy. You can see the attempt here, like historical data, all input. You've got it like you're building a model based on it, and then you're attempting to forecast new data after this or make predictions about how the world is going to unfurl, as a matter of fact, over time based on those historical trends. You see this most often, I suspect, used by quants in the finance industry. I can tell you that whenever I go give a talk at a bank about ontology engineering, they can never tell me what they're talking about for various legal reasons. And at some point I say, it's time series, isn't it? And then some young intern nods, and then everybody stares at them, and I'm like, I knew it. But yeah, I try to look. Just FYI, if you ever bring me out to a talk and I ask a question you don't want me to know the answer to, I'm going to be looking at the novices to nod or not. So FYI, just warning, time series, banks, Not surprising, but a little confirmation. In any event, Q learning, more or less reinforcement, an ML model for reinforcement that is. You can see the idea here being an agent takes actions, receives feedback, rewards or penalties, and then adjusts their strategies to improve performance over time. A baby might be a good example. State in action, they're crawling, they get a reward for crawling to a bottle, they continue doing it, they get penalized if they do something else like touch a stove. Pretty extreme penalization there, don't ever want to do that again. And they adjust their attitudes, their decisions, their behaviors based on that kind of reinforcement. Now, you can see in Q learning a strategy for teaching an agent to assign values to each action it might take, conditioned on the agent being in a particular state. So if you have like input of an apple and your computer system says it's a mango and you punch it and say that's wrong, it's an apple, it'll note it in these Q learning strategies, and hopefully when you give it an apple in the future, the reinforced response is accurate. It is in fact an apple, and it will say it's an apple and not a mango. Again, another exercise. Go navigate to the following location and play this little ArtBot game. It'll kind of combine a lot of the strategies discussed thus far. You can see where they work and don't. You can see where they might be applicable or not as you're trying to navigate or have this little ArtBot navigate a kind of wild west, as it were, of a museum. I'll give you a moment to type that in. Pause, blah, blah, blah. More me talking, not editing this out, just giving you time, and I'm going to move on now. So, into the depths of deep learning, which is again right at the middle and the bottom of this Venn diagram here. In the center, this subset of machine learning, subset of artificial intelligence. What exactly is deep about this? Well, not like anything in the profound sense. Instead, deep learning emphasizes learning of successive layers of increasingly meaningful representation. So it's not deep because there's some deep understanding achieved. Its depth is in terms of those successive layers. Now, what does that mean? So as other machine learning approaches focus on learning in few layers of data representations, deep learning involves structured layers stacked on top of each other. So most ML approaches aren't simple in using a single perceptron or single neuron. They usually do have like larger networks. Deep learning has lots and lots and lots of these hidden layers, lots of these networks all connected to it's quite deep. And you can see some inputs, outputs here. You'll have like an original input like this image, a bunch of hidden layers that kind of like take in information or carve up or decompose that image and like assign weights to like navigation through the network until it gets the appropriate final output. And I think there's something important here, at least like importantly reflective of our cognition as humans, that I do want to point to. And I'm not saying what I'm about to say to suggest that deep learning is how we do what I'm going to be describing next, but it is very interesting that machines can do what we do that I describe next. And what is that exactly? It's just this. Look at all these numbers. How is it that you recognize these numbers despite differences in shape? Think about that for a second. Different fonts. Like wildly different fonts. Look at the top numbers and the bottom numbers. Like how, I know 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 on the top and the bottom, but like, isn't it a little weird that you just kind of know that? They look so different. Now, if it's not weird, if you're just like, whatever, philosopher, blah, blah, blah. If you have children, it should be weird because children can do this very quickly. Like they learn to do this quickly. My daughter could pick out symbols before she was 1. Even in wildly different fonts. Like my wife walked in with this kind of like Panama City weird shirt on with like an M on it. And my daughter's name is Mira. It starts with M. She's known that since she was before 1, right? And so she could recognize M's. And see, this was some wild M on my wife's shirt. And she could pick it out. She knew it was an M. She said, M. And I was watching her. I was like, wow, that's kind of crazy. That's such a wildly different representation of the same symbol, and she's right. Now, how exactly does she recognize so quickly? How do we recognize so quickly, imperceptibly, without thinking about it, these numbers are the same. Look, neural networks transform images into representations of increasingly different from the original, but far more informative of the output. Deep neural networks then are like information distillation operations, where information goes through filters and comes out increasingly purified. And analogy here, when sufficiently scaled, the output can look like magic. Magic, like the way my 1-year-old daughter could identify an M in wildly different fonts. Like how? Maybe, I'm not saying like this. It is an odd observation, or an interesting observation, though, that we can do it with machines. So take this original input of that 4. You got a hidden layer. Layer 1, representations might be like snippets, like variations on that image. So like you just might get the tops of the 4 image. You might get a fuzzy 4. You might get lots of the lines in the first layer. In the second layer, you might get a lot of distortion, like, wild distortion, like different representations, different snippets of that image, different carvings of it, but like was, pulled out far or pressed too closely in or something. And then in the layer 3, it'll wildly distorted, right? Like I can't even make out 4s over there. And if you do that enough with enough depth and you figure out the appropriate weights that takes you from one layer to another, you can train a model that can accurately predict 4s in its various fonts. Machine learning involves mapping these inputs, like images, to targets, like 4s or cats, having observed many examples of inputs in the targets. Now, deep learning does this by input to target mapping via these deep sequences of data transformations, that is layers, where those transformations are learned by exposure to examples. Check this out. Wait, right, wrong, 7. Love this example, right? Like this GIF, you're trying to identify this image, and like these different characterizations in these different layers bring you to the right answer by identifying how to navigate through this complicated web of the network. Now, it's not exactly so easy here, because the specification of what a layer does to its input data is stored in its weights. Like remember the weights, right? Like that lottery ticket example. It's not just 1s and 0s. Like it's like a expected utility. Like I really want a lottery ticket, but it's only like 0.75 in my decision making. That's how much it's worth, and that's how much that weight is. In technical terms, we say that the transformation through this network is implemented by the parameterized weights. I can never say that word, so now I'm going to do it on a YouTube video, and everybody's going to know that I can't say that word. Parameterized by its weights. Weights in this, because of this, are sometimes called parameters of a layer. Now, what does this mean? Well, learning in this context means finding weights of all layers in a network, so the network will correctly map example inputs to target outputs. And a deep learning network can contain tens of millions of parameters, all those weights. Modifying the value of one of them may affect the behavior of all of the others. The fundamental trick here is to use a feedback signal to adjust the value of the weights a little in a direction that will provide more accurate output. And this is core, this to deep learning. It's the backpropagation algorithm. Which you see, you have hidden layers, inputs and outputs, difference, and then in the output layer you have a difference from the desired values, and then you have some method for going back and correcting the previous layers, those inputs from the layers, and then having ramifications in the adjustments of weights, so that themselves cause cascading effects to the rest of the network until it's back and forth, back propagation, until you get no or minimal difference in desired values. And so an analogy here, if you don't want to think through the algebra, is imagine you have a group of art students trying to learn to recognize the number 7 in different fonts. Each student specializes in looking for different features. So one might focus on straight lines, and another on angles, another on overall shape. Our art students would initially guess wildly. One student might say, I think it's a 7 if I see any diagonal line, while another might say it's only a 7 if it looks exactly like Times New Roman font. Backpropagation is like having a master artist who looks at their collective guesses and smacks them around, gives them feedback and say, no, that wasn't a 7, that was a 1, you fool. Student A, you were too excited about vertical lines. Student B, you need to pay more attention to the overall proportions. The students then turn around and adjust their criteria based on this feedback and then train again. That adjustment is in terms of their weight. So the students adjust based on the feedback so that over time the line specialist learns which lines matter for sevens, while the angle specialist learns the characteristic top angle and the shape specialist learns the overall proportions. The master artist feedback flows backwards through all the students. If the final answer was wrong, each student learns how they contributed. They might come up with rules like the following. If a node X encounters a strong diagonal line and node Y spots its horizontal top piece and proportions are confirmed to be correct by node Z, then we're probably looking at a 7. Training in progress. Now you can see the forward and backward direction. You have a 2. How do we get to 2? Forward, forward, backwards, backwards, corrections, adjustments, until we get the appropriate answer 2 or 9. Now this is, again, leading up to foundations of artificial intelligence in the modern era, machine learning, and then deep learning. This is all in background, really, so that we can get into MAL, which is a Python library that we will be using in this class to engage with deep learning and ontologies. So MAL, the machine learning with ontologies library, is used for converting our ontologies into graph data usable in deep learning. Training knowledge graphs are also within scopes that are embedding models under logical constraints, and then also evaluating models for axiom prediction, link prediction, or indeed ontology completion. Now, those are the stated uses on the documentation or in the documentation. For me, what I find practically useful here is that using design patterns to generate embeddings that can then be used for classification or clustering with MAL. Or if there are missing axioms, then training embeddings so the models can suggest missing links, or computing vector distances between entities to find, ontologically near items for mapping. I'll unpack that in just a moment. Or predicting novel instances of classes based on ontological relationships, such as like a sensor instance being predicted as a class and unit within an ontology embedding. So I find the MAL to be practically useful for these sorts of cases, which fall within the scope of the broad description you'd see in the documentation, but to my mind have more, a little more meat to them. So if you are following along in class, I strongly encourage you to go download MAL, install it, get it set up. It's probably going to take you a minute. It's not easy, especially if you're not using a Mac. They didn't make it very easy to use. We're going to use it anyway. Go forth, struggle with it. Come join us on the Slack so you can get some guidance. I will, in the interim, reach out to the folks, or have really at this point reached out to the folks running MAL so that we can maybe get some help and assistance. It can be done. I have run it. I can run it. I just know some of the students are having challenges. You will likely be one of them, especially if you're not using a Mac. In any event, I also, because of this debugging, I wanted to highlight some things that might make it a little easier or might make it more challenging. You choose your poison, but part of this course is debugging. I want to help you debug a little bit, or at least give you some guidance on that. So sometimes, especially when I'm like building a little lesson for a class, I want a reproducible, isolated space on my computer, so package versions for different libraries don't clash with anything else. So like if I want to download MAL or install it, I might want to use a specific type of or a specific version of Python, specific set of dependencies, and I don't want that to conflict with the general ones across my whole machine. So I might instead create a virtual environment right here, that VENV with Python, where I'm saying do this. What I'm essentially saying is create a virtual environment, which is a self-contained folder that holds its own installation of Python and its own packages. This command Python -env creates a private workspace named env that has its own copy of Python libraries and dependencies. And so what you get down here is I'm activating. So if I follow up on a Mac, I've got source env or env /bin/activate, and in Windows I've got env /scripts/activates. This is me following up with that initial command to create env environment and now activate it. Now, this is important if you open a new terminal later or close the terminal that you're using to create this virtual environment, you will disactivate it or deactivate it. You'll have to activate it again so that you can be in that environment if you want to use whatever you've stored in there. So when you activate it, your terminal prompt changes to show env at the very beginning, so it tells you that you're in that environment, and now every Python installation or Python command refers only to that folder environment. I will say, if you start trying to install things within that environment that you already have in the global space, it's likely you're likely to say, I don't need, or your output in your terminal will say, hey, you don't need to install this here, you have it in the global space. So if you have Python 3.1.2 in the global space and you're trying to install it in your venv or env environment, then it's going to say, hey, we don't need it, we'll just pull from the global. And so it won't be duplicating that if it can help it. In any event, activate this. And what you'll see is that in that environment, you want to install MAL. Now, MAL builds neural models over ontologies, and to do that, we need some more libraries. We need Torch, we need MAL itself, and we need OWL2Ready. Torch will be used for deep learning, PyTorch. MAL will be for the actual ontology, the machine learning bridge, and then OWL2Ready for reading OWL into Python. So within your env environment, this is the command that I use. You choose your poison wisely. I used pip install torch mal OWL2Ready. That got me where I needed to go, although I think some of the students may have needed to use mal-borg, so B-O-R-G, instead of mal itself. So just FYI. Now, before we write any code, we should confirm the libraries that we have are imported. I found it useful to use this command. Again, your mileage may vary. You might need to use something else to check. I tried this and it produced what I needed. So the Python command just tells the computer to use the Python interpreter. And if you're in an env environment, then it will use the interpreter that's in that folder that you've installed there. And then -c is the command. It says, this means in your terminal, run the code I'm about to give you as a string. So run the code. Everything in the quotes will be executed then as if it were a Python script. So this is contrasted with if I just put, something in quotes. I said Python, put something in quotes. The interpretation is going to be that it is a string of characters, something to read rather than to run. But what we want is something executable. We want to issue a command using Python interpreter. And in this case, it's going to be a command that says, load the MAL library into your memory, and then tell me the version number of it. So print, that is, now give me a string, print the MAL version using this version attribute from Python. And if you've done this correctly and your setup is working like it is on mine, then this command should return the version of MAL that you've installed in your directory. And so this is good, just a good sanity check before you write any code to make sure that you actually have MAL. If successful, you should see a printed version number. Otherwise, you might get an import error, and that means you might not be in the right environment or the installation of MAL failed. So MAL is designed to handle input in OWL formats. So MAL data set, as they describe in the documentation, contains 3 ontologies. They'll have a training ontology, a validation ontology, and a testing ontology. And each plays a role in how the model learns and tunes and then evaluates understanding of the ontology data that it's inputting. So for the training ontology, in this case, the ontology this is the ontology that MAL uses to train the embedding models. It contains axioms that define a semantic structure you want the model to learn. So here's a simple example. Dog being a subclass of mammal and mammal being a subclass of animal. So what MAL does when it's reading this in is it converts all logical axioms like those above into sets of triples, so subject, predicates, objects. And then it uses these triples to train a neural embedding. I'll talk about what an embedding is in just a second, but basically related entities like dog and mammal become geometrically close in a vector space. This is the information that the model sees and learns from. So the training ontology is what the model that we're trying to train sees. This is the data we give it to train on. Here's a toy training ontology that I put together. So in the repo, Mal will turn such logical statements into training constraints. So an owl is a class, or an animal is a class, a mammal is a class as well, so is a dog. And mammal is a subclass of animal, and dog is a subclass of mammal. Now we need more than just the training set because we want to make predictions about, say, new links or new connections, and so we need a way to like correct and fix our training set because it's not going to be accurate just as is. We're not going to have enough data, or we're not going to get us to a place where we can make inductions about it. So we do need a validation ontology, something to kind of reinforce the learning. So an ontology here can be used to check whether the model is learning effectively, and it might contain subsets of axioms that are extracted from the training, like subclass or property assertions that we don't keep in the training ontology. And so what Mal will do is after each training session, Mal tests the model's predictions against the validation ontology. And so a validation score given will guide adjustments and learning rates and how big the size of the vector space should be. And it'll help us determine when to stop training. That is, once we keep hitting all the validation marks, we stop improving. And this is used for fine-tuning models, not exactly for training them directly, just for correcting them. An example toy validation ontology is something like a cat being a class that's a subclass of mammals. So this would be held out of the training set. This would be put into the toy validation set, and what we'd be doing is whenever we get outputs from our training, compare and see if we can get this kind of axiom, get that a cat is a class and a subclass of mammal from what our training set was, or something close to it. Now, the testing ontology, this plays a role in the evaluation of our understanding of the ontological structure. And this essentially tells us that we can generalize when we get correct. So the testing ontology is used after training to measure how well the model generalizes to unseen data. So if the model learned that a dog is a subclass of mammal, or dogs are subclass, or dog, the class, is a subclass of mammal, and mammal is a subclass of animal, then the test ontology might include things like dog being a subclass of animal, which is a logically implied axiom through transitivity of subclass. What Mal will do is evaluate how well the trained embeddings predict withheld axioms. And it'll produce metrics like how highly the correct entity is ranked and how often the correct relation is among the top predictions. This tests the model. These are tests that the model has never seen. The data the model has never seen, and they're used to report final performance. A test case, just a toy test ontology, logical relationship of the sort that should be inferred, not seen during training. Now I wrote this little script putting together running Mal. It was a simple one. Basically, see this, you can probably write your own. What I'm going to do here is I'm just going to walk through some of what's going on here so you have an understanding of what Mal is doing. So this first reads a toy train turtle file and parses axioms into triples for learning. That's what that is, just a path check. Also, I started like a Java model at the front. At the beginning, you're probably going to have to do the same thing, and kept throwing errors if I didn't put that in. In any event, so what we have down here is I'm defining a model as this connection of an EL embedding function that takes blah, 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 blah. What is that blah, 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 blah? What are these embeddings? I hear you cry. Let's focus on this first. So an embedding is a way of representing symbolic things like words, images, or classes in an ontology as vectors of numbers, like points in a geometric space. For example, the word king might be represented as 0.12 or negative, common negative 0.3, 0.8, and so forth. So this vector space is this little matrix, or the class dog might be represented as a matrix as well, which again has a corresponding vector space. Each of these numbers corresponds to some dimension in a geometric space. And if the embedding, as we described in the code there, is size 16, then what that means is that each class is represented as a 16-dimensional vector. So 16 dimensions. So we know how to think about 1 dimension, 2 dimension, 3 dimension, 4 dimension, I guess. I'm a 4-dimensional thing. I'm existing over time. So time series might count as that. What's a 5-dimensional dimensional vector? I have no idea. What's 5D space, 6D space, let alone 16D space? Thank Descartes for algebra. And its relationship to graphs. I have no idea how to think about it geometrically. I don't know how to draw that thing, but certainly I can write matrices that reflect it and then run computation over them, decompose them, etc., place them in space regardless, or at least calculate how close they are to one another. What's going on here is there's embeddings in a dimensional space for each of these terms, each of these words, the kind of targets, the things that we'll find interesting like axioms and classes and relations, and we'll put them all into a dimensional space, in this case 16D, even if we can't imagine it. Now, we'll also be running training on those space. The training loop is where Mal learns the embeddings by iteratively adjusting them. So we'll train, in this case, 6 times. We'll run through every class starting with a random vector. So we'll assign random vector space, like we'll place them in the 16D space randomly, all the classes, and then each axiom will become a training pair that there's a constraint that the model must satisfy. So we'll then score and estimate how well each pair fits, that is to say how close dog is to mammal. And we'll update the model vectors to minimize loss. So we'll make dog, in our training, we'll aim to make dog closer and closer in that dimensional space to mammal. Again, starting off, dog can be way over on one side of their 16D space. Mammal can be way over on the other. We'll use axioms to help train our models so that as we run through training again and again, the dogs are going to get closer to mammal in that space, so their vectors will change. And with each pass, those vectors will settle into positions that best represent the logical structure. And this is where we're going to learn embeddings that encode semantic structure that mimics or mirrors the ontological logic. And this should sound familiar. This is that backpropagation work on display. We're training so that we can get these vector representations closer together to reflect the logic that we know and love. Here we'll see, we'll return this 6-dimensional vector. And then after training, we expect to see something where the dog, like the kind of similarity, that is to say the representation in space, this vector space of dog is very close to mammal, mammal is very close to animal, and dog is at least positive or nearby or somewhat close to animal in that space as well, and that being the inference that we were going to check in our testing. So every dog is a kind of mammal is expressed by placing a vector, in this case, for a dog close to or inside a vector for a mammal in that vector space. And so that kind of expression there, that cost that we'll hear about later, what that's doing is checking how geometrically close 2 classes are in this space. And so it's not just classes and subclass relationships that we can check with MAL. You'll see that subclass here, the logical relation on the one hand has a geometric analogy where a vector or region of A is contained within or near B. Similarly, disjointness can be represented where vectors are far apart or non-overlapping, and then equivalence where they're nearly identical in geometric space, and relations where the vector of one plus some offset is roughly speaking the vector of the other. Now, I want you all, whether you're in class or not, to set up your MAL environment, because that's key. And then I want you to navigate to the course GitHub page and download the training ontology and the test scripts that I put. So the stuff that I just was talking about, it's in a MAL-demo repository on the Ontology Tradecraft GitHub repository. It's open space, so check it out. And I want you to go download that information and ensure you can run the script and can return a test score like I was describing a minute ago. Now, what you'll see, if you can do this, and I'll pause, of course, as I should, let you do it. Go do the thing. I'll just blah, 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 say nonsense. You do this, set it up. Really, you should pause the video. But then what you should see when you run this successfully is you're going to have training data sets. These numbers summarizing how many logical axioms MAL extracted from your ontology. And you'll see there are codes. So GCI 0, logical pattern is subclass inclusion. Now, our patterns were simple. We had subclasses, so we didn't do anything more sophisticated, but you could. So GCI 1 is classes with existential restrictions. So everything is related to something. Every A is related to some B. You have GCI 2, restrictions on the left. You have things that are related only. And then on the other hand, you have GCI 3, You have intersection inclusion, where A and B intersect under C. And then, of course, you have GCI star bot, which is where you found something inconsistent. So hopefully you won't have much of those, but if you do, there it is. You'll have a code for it. Now, an epoch in this case means one full pass through the training. So the two subclass axioms, for example, that training data, just the two subclass axioms, and each epoch computes a loss, which measures how far off the model's current embeddings are from what the logic requires. So embeddings in that vector space, how far are you off from what the logic says should be true? Then that model represents each class as some 16 by 16 vector, and each vector is adjusted so subclasses sit inside their superclasses in that space. And as you can see, as we run through the epochs, 1.21, as we train, we get closer and closer to 1.16, where we're trying to aim down to 1 or as minimal as possible to get that training loss down. And the result, we can get each number given a cosine similarity, which I'll talk about next week, between two vectors in this embedding space. Essentially, like if you're thinking of vectors pointing off into space, how close are they together? Like what's the angle between them in terms of closeness? Like you have like 90 degrees, 180, they're not related at all, or they're somewhere in between. Dog mammal should have pretty high. So 1 means identical vectors, -1 means opposite and totally unrelated, or like total opposites, and then 0 is just completely unrelated. Here we have dogs related to mammal, that similarity between them being quite high, which is what we would expect. Mammal and dog as well. Mammal and animal as well. And then dog and animal being the thing we're trying to check to see if it could be inferred, pretty high too. Done. Model trainings and embedding computed. So on this initial run, first exercise here, using the training ontology, is just to emphasize how it works. During the next session, we'll add validation and test ontologies to measure how, or at least validation and test descriptions to measure how well the model generalizes. And then I'll let you get a head start in that on project 5. Now, summarizing here, just in case, I showed you how to create an ENV and do them install with MAL, load ontologies, train, inspect embeddings, and then MAL turn AL axioms into a trainable representation whose geometry reflects semantic structure. Everyone should now be, by the end of this, able to run MAL locally and is primed to plug it in to the semantic pipelines we've built in previous lessons. With that, go forth and MAL it up. I'm sure there's something clever to say there. Fill it in at your leisure. I'm tired of talking. See you next time.